Hey everybody, welcome back to MLFL. Today our speaker is Aaron Mueller from Boston University. Aaron is an assistant professor of computer science and by courtesy data science at Boston University. His research centers on developing language modeling methods and evaluations inspired by causal and linguistic principles and applying these to precisely control and improve the generalization of computational models of language. He completed a PhD at Johns Hopkins University and was a Zuckerman postdoctoral fellow at Northeastern and the Technion. His work has been published in ML and NLP venues, such as ICML, ACL, and EMNLP, and has won awards at TMLR and ACL. He's a recurring organizer of the Black Box NLP and Baby LM workshops, and has recently been featured in IEEE Spectrum and MIT Technology Review. So without further ado, please give a hand for our speaker.
For the introduction. So it's really nice to be back here again. One of my first ever NLP research experiences was as an undergrad intern here at UMass Amherst as an NSF-RU fellow. So now that I've gotten a bit more experience under my belt, it's nice to actually be back here and like sharing some of the things that I've been working on since a long time ago. So I want to start by bringing attention to this pretty pivotal work by Jeffrey Hellman back in 1990. So in this paper, Jeff Hellman introduced the recurrent neural network, which would dominate natural language processing research based on neural methods for the following couple decades. And his key insight was that the really important part about language is the fact that it is temporally structured. So language cannot be decomposed into a series of parallelly processed like bags of words, for example. You actually have to directly model this time dimension to get the best possible performance. And this seems pretty obvious in hindsight, but it actually was something that was not really often directly interfaced with back when he was making these arguments. So of course, language is a temporal medium, that's like the fundamental in the day. So given a sentence like this, for example, if you read the sentence up to on the binder, you might initially think that the goal was to put the force onto the binder. So you have this kind of distractor target. But when you read the rest of the sentence, you actually realize, oh, I was supposed to put the force onto the scarf instead. When humans are given this task, like we shouldn't just be able to do it without even knowing there was ambiguity in the first place, because it gets resolved so quickly. But what's been found in neuroscience research, like in this Su et al. Paper, they found that there is this conscious cognitive control mechanism that's employed in examples like this. What it does is overrides the prior interpretation and increases probabilities corresponding to the new interpretation. This mechanism would not have been necessary if not for the fact that language was temporally processed in sequence. Similar examples come from things like garden path sentences, where initially you might think that the sentence implies that the postman is maintaining the mail directly. But upon receiving the rest of the sentence, you realize this is actually a reduced relative clause. So they are really maintaining that the mail is gone, completely changing the meaning of the sentence. This is a pretty obvious example, but the main thing I want to highlight here at the end of the day is that language has to be processed in sequence, and this explains much of the mechanisms underlying how we handle this media. So language models, of course, being models of language, do pick up on the structure as well. Of course, one can no longer naively assume that representations in LMs are not temporally sensitive. So here, for example, you see that the intrinsic dimensionality of LM representations increases with time. Whereas if you assume this like stationarity surrogate, where you simply randomly shuffle words and then give it back to the model, this has no meaningful increase or decrease in dimensionality as you go along the sequence, which is sort of indirect evidence that it is picking up on the structure directly. Other evidence comes from the fact that LMs can handle long distance dependencies without a whole lot of issues anymore. And that this surprisal is at least used to correlate really well with human reading times, although this trend has kind of reversed in recent years as LMs have started to become better than humans at predicting real words. So the question that underlies a lot of interpretability research when faced with questions like this are what concepts actually underlie the ability of language models to do these tasks well? And how are these concepts composed to perform these complex tasks? So in this talk, I'm going to be presenting two really common paradigms in interpretability research aimed at answering these questions. The first paradigm is going to be the circuit discovery paradigm, where we aim to basically discover these causal subgraphs of the computation graph that implement some specific task behavior. The second paradigm will be focused more on qualitative understanding of what concepts the models have actually learned to represent and how they deploy those in practice. So the main claim of my talk is going to be that interpretability today is where language modeling was before 1990. That is, we commonly assume that every component in a model has the same functional role at all positions. And it's common to assume the structure of the causal graph, all implements do some task, is totally stationary with respect to time. That is, the structure of the graph is going to be the same at all possible positions for a given task input. So today's project is going to be some time-aware methods that improve upon this state-of-the-art right now in a way that's meant to incorporate this temporal structure. So the way I'll structure this is I'll first go over this circuit discovery paradigm because I think it forms a bit of an easier introduction to the basic ideas of the field. And then I'll talk in a bit more detail about how we find time-varying conceptual representations and show some applications for those. And I'll end by showing some qualitative case studies where we analyze how language models process things like garden path sentences and detect event boundaries using these feature representations. And feel free to interrupt and ask questions at any point in the talk, by the way. So what exactly is a circuit? So what I have here is a schematic of a language model. You have, say, 3 hidden layers here. And in each of these layers, you have this branch out to the attention heads, these squares, and the MLPs, or these orange circles. And the representations from the output of the MLPs get added back into the residual stream here. The goal of circuit discovery is to find this subgraph of this computation graph that implements the specific task behavior. So here the example is a garden path sentence, which has multiple possible conclusions. The salesperson sold the car. Given this context, you probably would assume that sold is a simple past verb, where car is the object. But you could also interpret it as a reduced relative clause. So the salesperson who was sold the car smiled, for example. These 2 different parses have different expected completions, and so you could feasibly predict either and still be correct in some grammatical sense. So what we want to do is locate something like the subgraph that explains in which components this sentence is being processed, and which components actually cause the probability of one or the other completion to increase or decrease. So this could, for example, give us something like this red subgraph, which decreases probabilities and corresponds to the interpretation of sold as a simple past verb. But the blue components correspond to the interpretation of the sentence as being dominated by a relative clause. So how do you actually discover something like this practically? Well, this can be sort of done using the framework presented in causal mediation analysis. So in causal mediation analysis, you typically have some component that you think influences the output and some target metric. What you can do is define 2 minimally varying inputs that differ only with respect to one of these input features, but which then causes the output answer to flip, ideally. So in this case, we have this indirect object identification task, where the goal given the sentence is to predict John, the correct indirect object of this verb. But then we can also have a counterfactual input x tilde, where the answer is flipped to Mary. So what we can do here is start by computing the causal importance of any given component, like an attention head, an MLP, a feature, anything really, by setting its activation to what it would have been given this counterfactual input, but we're giving the original input to the model. So we're just doing this intervention to one component and computing how much that intervention changes this output metric, this probability difference between the 2 completions. The idea is that if this component is causally relevant to doing this task well, this metric should significantly change when you do this intervention. Conversely, if this component is irrelevant to doing the task, then this IE metric or this indirect effect should be basically close to 0 because it will have no impact on the metric at all. Now, as is, this exact patching approach is basically intractable because you have to loop over all possible components and do this patch separately. So in practice, we use a gradient attribution instead. You can think of this like a linear approximation to this exact patching metric, where the gradient of n with respect to this activation is like the slope. And the activation difference corresponds to how much you move along that line on the slope. And the nice thing about this is that you can compute these gradients and activations all in parallel. So this gives you a constant time algorithm that gives you the importances of all of these components in the model, given a certain input. So once we have all of those attributions, we'll compute them across all token positions in the sequence. And then afterwards, we'll sum those importances across positions to get the indirect effect of a given component overall. And if that indirect effect metric is above some threshold, which is a hyperparameter, we'll then include it in our circuits. So what this gives us at the end of the day is a circuit that looks something kind of like this. Because we've aggregated our importance scores across all positions, we don't really have any notion of at which positions these components were actually important for doing the task properly. So in other words, we have assumed the stationarity of the causal graph.
And what happens here is that you have this graph that looks exactly the same in all positions, and a graph that is fully connected across all possible positions. So this seems kind of like blatantly wrong, right? Like it seems clear to at least a human that the kinds of thinking you have to do will differ pretty significantly at every point in the sentence. Whether you're detecting what the subject is, what the verb phrase is saying about the subject, and then who's being given like the object in the sentence. So thinking more specifically about failure modes here, you could imagine things like low recall on the left example here, where the same component is always kind of harder because it's very small numbers. This yellow component on the top has a really high importance at the third position, but then an equally high but negative contribution in the second position. So clearly it's doing something really important, but when aggregating across all the positions, this totally cancels out. So you end up not including it in the circuit at all. On the right-hand side, we have this other issue where components have like very, very small influences across all the positions. But because of this aggregation, we end up seeing them as actually being important to the task, even though at any given point in time, they're not really doing all that much. So this causes us to have both low precision and both low recall as well. So what we ideally like to do is do something more like discovering a position-aware circuit. So this paper was presented recently at ACL and was with these folks at Technion here. And you can see here that like the data structure probably more closely resembles what you would expect here. You can have different components at differing time steps. And you can have like different edges to different components across those time steps. So there's no longer any kind of assumption of fully connectedness across positions, nor any assumption that the same components will be used at all positions, which is nice. But this introduces a couple of methodological challenges here. So the first challenge is, how do you actually align these positions across the examples? So typically what you do is you average these importance scores over many examples from the task. But if the same information is at a different token position for every example, you can't really preserve that semantic span information very easily as is. Like maybe the subject Mary will appear like the fourth token in one example, the sixth token in another. So you can't just like align things via token positions themselves. The other challenge is, how do you actually compute these cross-positional edges? Traditional methods provide no real way of doing this, so we had to devise something more original to actually address this challenge. So for some tasks, this is actually quite easy. When you want to align information across examples, some tasks are completely templatic, or have what we call full alignment, that is in this top example. So in the greater than task, which we experiment with, we have things like nouns, which always appear in the second position. The rest of the phrase is always exactly the same, lasted from the year blank to the year blank. And the only things that are varying here are the choice of noun and the exact numbers used in this task. The goal of the model here is to predict any kind of latitude numbers that are greater than this previous numerical suffix, thus making the sentence logically valid. But in other tasks, it's not really so easy. In tasks like indirect object identification, you instead have what we would call partial alignment. And this means that the spans here always appear in the same order, but you don't actually always have the same number of spans, nor spans of the same length for any given input. So for this IOI task, you can see that sometimes there's this prefix word before the subject appears, but in other inputs, there's no such prefix. Sometimes you have this like first action that went to the store or left the concert, but these could have different token lengths. So alignment here becomes a little bit more challenging than in a full alignment setting. So our goal was to actually devise some way of automatically producing these semantic alignments across examples, such that we can better average across all of our examples. Note that we also experiment with this window bias task, which is somewhere in between these two. It's generated templatically, but these actions have like pretty highly varying sequence lengths. So we use this as more of like a more impactful test case. So the idea behind spans is that once you have them, you can pretty easily map back and forth between the abstract computation graph defined by the spans to the full computation graph defined by token positions. What we're going to be assuming is that within any given span, every token position within that span is basically fully connected to the extent possible. So if you include some component in the first layer, that component will always be connected to itself at all other positions within the span. So we're basically ensuring that information will always be able to flow between all positions within the span. This probably is not a correct assumption, but we just wanted to make sure that we weren't losing any information unnecessarily here. So we're sacrificing a bit of precision to gain some practical utility here. So how do we actually generate these schema then? So what we can actually do is just have a language model do it. So before you get mad at me, we did actually validate this against human-generated schema, and it works just as well, but I'll get there in just a second. So what we tried doing first was taking a bunch of examples from the task and just handcrafting schemas that corresponded to like the structure of the task. So for IOI, for example, we had this handwritten schema that we wrote ourselves. But you could also just pass the inputs from the task to the model and then have it generate something by itself. So in practice, that doesn't actually work very well as is. So we had to add this binary mask as well to tell it which positions were really important for drawing span boundaries at. This mask was obtained by doing gradient attributions to the input tokens and then discretizing them into a binary mask. Basically, if the attributions for a given token were greater than this 1 over n value, the length of the sequence, then we made it 1, otherwise it was 0. So tokens that have some really clear pivotal role should be tokens that we should draw a span boundary is the idea. In practice, this massively improves the quality of the schemas the model generates. So the output of this process is going to be basically a JSON that corresponds to these like semantic labels that seem to explain the structure of the task for any given example in that task. We usually give it somewhere between like 10 to 20 examples at a time for drawing these schemas out, and then we test them later by simply looking at how faithful the circuits are using these schemas. Then given the schemas in an example, you have to also apply it to the examples. Manually doing this is really challenging, so we again just have an LLM do it for us. So what this should produce is the labeled sentence, where every single item is split according to these span boundaries. We did have to throw out a few examples where the spans were applied incorrectly or in the wrong order, but we were able to preserve usually an order of like 80 to 90% of the examples where it drew the schemas correctly. So challenge 2 is drawing cross-positional edges. As is, there was no method that was actually natively able to do this. So we defined this approach based solely on the attention heads and their relationships to each other. So here what we're doing is basically approximating how changing the keys or values in some earlier position head would have influenced the output of some later position head. So there are 3 different ways you could imagine doing patching here. The first of them is just patching the value and then seeing how that changes the output of the head. Or you can patch the key of the earlier head and see how that changes the output of later head via this new key query operation. Or you can just patch the query at the later position and see how that changes the output of the head while holding the original one constant to what it would have been beforehand. So this defines 3 different patching operations. And if any of these give like some change in the output metric that's greater than some threshold, we include it in the circuit. I won't really show the math here because it's a little bit involved, but if you're interested, I'd be happy to go over it in a bit more detail. So for our experiments, we'll be using 3 tasks that I've already shown here, greater than IOI window bias, and our main evaluation metric is going to be faithfulness. Faithfulness is among the more common metrics used in this field, and it's basically defined as a notion of how much of the full model's behavior has your circuit captured. So we have 2 versions of it here on the right-hand side. We have soft faithfulness, which measures the probability ratio between some correct token outputs, given only the circuit versus given the full model. The idea being that a ratio closer to 1 is going to be better in general. Hard faithfulness measures mostly the same thing, but now we're just measuring whether the actual like argmax token from the full model versus the circuit are exactly the same. And note that we subsample 2 examples that the model got correct. So this is always going to be the correct token in this instance. So our hypothesis is going to be that position-aware methods, if positionality is actually important, should achieve higher faithfulness at much smaller circuit sizes than non-positional methods. And the experiments do bear out this assumption. So what I'm showing here is on the y or the x-axis, we have the number of edges in the circuit or the circuit size. And the y-axis is the hard faithfulness metric, how often the circuit gives you the exact same answer as the full model at that circuit size. So the gray line on the right-hand side of most of these graphs is the non-positional circuits. Ideally, what you should see is a really high area under the curve if your method performs well. But what we see is that the method with the lowest area under the curve is always the non-positional circuits. So even when your schemas are not particularly good, as when the LLM without the mask examples, we still get huge gains in efficiency and conciseness of our explanations by simply incorporating positionality into our explanations. Furthermore, when you look at the difference between the LLM-generated schemas with and without these binary attribution masks, those with the masks perform far better in practice. So it seems like having access to these like positions the model knows are important is going to be helpful for drawing these schemas. And finally, if you compare the best LLM-based method to the human, the yellow line here, you can see that in most cases, they're basically the exact same line. So this tells us that this LLM plus mask approach is often just as good as handcrafted schemas. which we found pretty surprising, but it's also pretty encouraging for this research paradigm, I think. So results are also pretty consistent when using soft faithfulness metric as well. You do see this like really weird dip pattern with the window bias on the far right here. I think mainly because there's like this distractor token that is also valid if a model encodes gender bias. So once you achieve only the components that actually encode the gender bias, you have this like negative phenomenon. But once it gets enough components to override its gender bias, it goes back to producing like the expected correct answer. So for the most part, we see the same trends otherwise though. Using masks is helpful and gives you schemas that are just as good as human-generated schemas. So the main takeaway here is that by merely incorporating positionality and positional variance into our methods, we're able to significantly improve the concision of our explanations and get better explanations at smaller circuit sizes. Schemas seem like pretty good ways of going about this, but unfortunately they are currently a bit limited. We had to make this assumption that the schemas will always appear in the same order in any given example, and this seems kind of blatantly untrue for most tasks that involve like more complex kinds of reasoning. So future work really should investigate like ways in which this could be made a bit more automatic and flexible. I think one surprising finding here is that the LLM-generated schemas work so well. It seems like humans should have been better able to deduce the structure of the task because we had access to the Python code that generated the tasks in the first place. But LLMs were able to induce this pretty well. And it's possible they may have actually seen the task themselves in the training corpus, so we didn't control for that. But at least for the tasks that we investigated, this seemed like a pretty good approach that could be mostly automated away. So cool. That seems like incorporating positionality already is known to be helpful, but in hindsight, this seems a bit obvious, right? Like we know that language is temporal now, so incorporating this actually seems to help. I think what we actually care about is more of a qualitative understanding of what these features in the circuit actually are, and how we can improve our understanding of what the models are really implementing algorithmically via this temporal understanding. So before I go into like feature explanations, were there any questions about this first project?
Oh, just what was the model architecture? Was it an RNN or?
Yeah, so we experimented with GPT-2 small and with Llama and Gemma as well. So all transformer LLMs, autoregressive.
Okay.
Yeah.
So when you said that the non-positional circuits are fully connected across time steps, is that what edges are possible in those scenarios? Like for example, can you have backwards edges like from D to D minus 1?
Yes, I should have said like fully connected under the constraints of the computation graph, I should say. So on every edge that goes across positions in the computation graph, which you could abstract a way to think is something like everything that goes like from left to right basically, would implicitly be included in the circuit here. Because all the information is simply allowed to flow across time positions without any kind of controls as to like where it's flowing to in those cases.
Good. Go ahead.
Oh, I have a question about the human baseline. Like for the human baseline, do you mean using the human defined schema, but still use the gradient attribution patching? Or
Yes. So in all cases, we are using gradient attributions for our experiments. So here, like the only difference is in like how the task is like semantically divided when drawing the circuits. Like, do you assume that everything in the first, like, I guess prefix is like one span? Or do you assume that it's like the whole first like half of the sentence, for example? So like when drawing these like schema boundaries, it's possible for you to draw like very different kinds of boundaries. Like maybe instead of separate like S and IO spans, you have like a one like S1 and S2 span, for example. Like that's also valid. Yeah.
So looking at the graphs you were showing, the x-axis takes us up to large numbers of edges. Can you give us a sense of what percentage of the model is really being included in that circuit?
Yeah, so on these graphs, the right-hand side is always the full model. And so the distance to the right-hand side tells you like what percentage of edges are being included here. So yeah, like it looks like you typically need something on the order of like 2 to the 5th edges to actually get anything close to good faithfulness. And from then on, it's like very diminishing returns. It seems like you sort of constantly need like doublings of components to get like a doubling in the percentage of what you've recovered after that point. But most of the gains come from this initial like, very sparse circuit, it seems like in most cases. Yeah.
Have you thought all of it like more abstract, sort of, I guess, semantic graphs here, like using, rather than like these very templated tasks, like, okay, we've expanded to like certain spans, like can we use like the features themselves to define like more abstract spans or whatever?
Well, like basically going back to like the design of like the circuit in the first place after we understand like what works well, something like that. Like an iterative like approach.
I guess this is that question.
Well, I think it's a lot of people thing to think about. Like, I think if we understood qualitatively what was in the circuits, that should probably inform how you split up the spans. Because it seems very possibly unlikely that like the true computation of the model will not resemble like how a human would have done this task. And right now, like, with these human crafted schemas, like we are sort of presuming a human likeness in the mechanism. But maybe the model actually is doing something totally different that we're not really anticipating. And if we were able to better approach that, we would get better scores probably. Yeah, so I think that the actual like qualitative understanding would be pretty important. But circuits as is don't really directly provide that to you for reasons I'll mention in like a couple slides. Cool. I think that segues pretty well into the second part here. So cool. Now let's assume that we have this really nice position-aware circuits. We now have an understanding of which components are in this computation graph and which ones seem to be doing the task. But the issue is, like, once you have the circuit, like, what can you actually do with it? And the answer as is not very much. The reason for this is because every component in the circuit probably will not be understandable to a person. Because usually components in computation graphs are doing many different things at the exact same time. This is because representations are distributed, such that one neuron can be doing many things, and one concept can be distributed across many neurons, giving us this many-to-many relationship between model components and concepts. So actually, the circuit is not super faithful as is when based on model components to the structure of the model's computation. So this actually references a pretty classic debate in the field of deep learning that goes all the way back to the beginning of the field. The localist assumption that we've been implicitly making so far says that there should be one computing element for every conceptual entity in the computation graph. Whereas in distributed representations, there's more of a many-to-many relationship. So every computational element could distribute like many concepts over itself, and you could end up with this space that has like even more concepts than there are like model components in the first place, because you can put them all off the true like neuron-based axis. So this is kind of a challenge for us, right? Like if we had localist representations, things would be much more interpretable and much easier to edit post hoc and steer with. But it would also be far less parameter efficient, because you would need to assume that you have enough parameters for every single concept you care about, or even combinations of concepts. Distributed representations, on the other hand, are far less interpretable, but they have a lot of practical benefits, like being totally continuous and gracefully integrating under relations and steering operations. So because of these practical benefits, most of our models today would have distributed representations. So the question now is, should we actually even expect anything interpretable or human-like to be in these models whatsoever? And the answer from recent work seems to be yes, but it's not going to be simple to find them as simply localizing to neurons. So to look at distributed concepts, we have to go off the neuron axis. So here I'm going to briefly summarize a recent survey that we published in Computational Linguistics, which summarizes this idea of like, what's the best unit of analysis for understanding model computations? If you're interested in more detail here, please do feel free to check it out or ask questions about it later. So given this language model again, how do we find out like which components were responsible for like parsing this picture of a cat and generating the proper completion to this caption? If the true cat concept lies off the neuron basis, then you're not going to be able to use any particular neuron to isolate it. You need all three to some extent, but you actually need the right weighted combination of all three. So what's typically done in these settings is you can train something like a probing classifier, where the weights of the probe define the weights in this linear combination of each of the neurons' directions. And sparse autoencoders, which have recently become popular in the field, do much the same thing. Only the nice thing about SAEs is that they give you a ton of these weighted combinations. Typically, you would expand the dimensionality of the features by like 16 times, for example, giving you something on the order of tens of thousands of features for any given activation vector that you're expecting. So because of this benefit, and because we no longer have to assume any kind of human likeness in the conceptual space, SAEs have become very popular. So the basic idea is that you can decompose this activation vector into a sparse vector of features, where by feature, I think we need a single dimension in this vector F. So every given neuron in this like red vector would be like a separate feature that you could inspect, and which could feasibly be our cat feature in this instance. These models are usually trained with a very simple loss to simply reconstruct the original activations with some sparsity penalty. So something pretty simple. Here in this next part, I'm going to be factorizing it a little bit differently. I'll be referring to this D matrix as the dictionary, the thing that maps the input activations to the concepts. And Z will be the coefficients on the dictionary, which define for any given input how strongly that concept is going to be active on this input X. And then we have the same regularization loss as before, this R term. So now I'm going to be presenting some of the novel points here that incorporate temporality into these feature representations. So think about how you would actually parse a sequence like this. My collaborator is a big Harry Potter fan, so we'll use this example for the purpose of the demonstration. As you read more and more of this input passage, you see that there's like this increasing complexity of information that's being built up over time. Once you have this context about this character, this information is pretty stable and doesn't change very quickly. But at every single individual time step, you're always introducing novel contextual information that is being added to this slow-moving contextual representation. So if you decompose this into something like an SAE vector, what we would have assumed is typically that there's going to be the same number of latents active at any given position. So a common method these days in the field is like top K SAE encoding, where this always assumes that you only need at most K dimensions in this vector to explain the entire activations of what's happening here. But this assumption seems also, again, pretty wrong. It seems weird to assume that we're always going to have this constant sparsity constraint. Really what it seems like we need is an increasing complexity and decreasing sparsity with time. So we can try building this inductive bias into our autoencoder and seeing if that gives us any features that are more interpretable than what we already have. So being more specific about this, if you imagine that this representation sequence changes over time along a specific conceptual axis, we simply are factoring out that conceptual axis at every time step from the novel information and putting it into this dense contextual representation. And we'll treat these two things as separate objects for the purposes of this study. So let's actually go through these two assumptions and see like why they're kind of problematic and why we need a new method here. So this first assumption that was implicitly there of constant sparsity seems pretty wrong. Returning to our figure from the introduction, as you increase along the time dimension on the x-axis here, the intrinsic dimensionality of the representations of an LM seem to be increasing dimensions. Conversely, this sort of surrogate, where you randomly shuffle the tokens and give it the exact same sequence, has this constant sparsity. So only if you assume that there's no meaningful cross-temporal dependencies can you assume constant sparsity. But in realistic settings, you do have to actually account for the fact that there's this increasing number of dimensions that are needed over time. The other assumption here is the exchangeability over time of each representation. So we've also assumed implicitly in our loss term that you should be able to take any concept at any position t and simply swap it out for the same concept at some other position, like t+1 or t-1, for example. If that were true, then what you would expect to see is that in this figure on the right, you should see sort of a horizontal striping pattern with respect to positions. So basically, the amount of this new information you can explain with the prior window, let's say 30 tokens, for example, should be constant regardless of where you are in the sequence. So there's sort of an invariance with respect to this x-axis here. But in practice, what we actually see is that they're not exchangeable at all. You have both this vertical and horizontal phenomenon, where more and more of the current position can be explained by the context as you get further into the context. So this seems to suggest that this x-axis actually is kind of important to directly model. So we're going to be doing is proposing a new architecture for decomposing representations into features. The first part of this proceeds much like before. We have some tokens T, which get encoded into language model activations X, and then those get encoded by our dictionary into these latent feature representations of V in this case. So much the same as before. But what we'll do now is for every current time position, we'll use an attention mechanism to decide which information from the context is going to be helpful for explaining the current position. And what we'll do then is we'll subtract off this contextual information from the current position. So this contextual vector is what we'll call this like dense predictive or contextual representation vector. After we subtracted off this context from the representations, we get this more novel bit of information. So the idea here is that the novel information should be orthogonal to the contextual information because it should be information that has been introduced only at this new time position and not in prior sequence positions. So the hope is that these two will be very dissimilar and that only the novel one will encode, much in the same way that an SAE does, the information being encoded in the new position because it will be sparse. So note that this contextual representation will likely be dense and not be as interpretable as the sparse representations for the novel vectors, but in practice, they can be rank sparse. So let's just maybe sanity check this architecture and see if it works as well as prior SAEs before we do anything else with them. So one common evaluation metric in the field is variance explained. Here what you would do is simply reconstruct the activations X at the output of your SAE and see if you captured most of the variance across examples in your data set. And it looks here like the novel codes are reconstructing about as much information as the SAEs, and that in combination with the contextual vector, it's getting the same performance as the state-of-the-art encoding approach here. So nothing is really being lost compared to prior approaches. We're simply factorizing it a bit differently now. And as a sanity check, we also do see that the two codes that we generated are pretty distinct from each other in measurably interesting ways. So to be more qualitative about this, we can first inspect our novel codes, because this is what we expect to be basically the same as prior SAE approaches. They're sparse and should therefore be a bit more interpretable than the dense representations of model activation vectors. This is probably kind of hard to see with the text being so small, but basically each column defines a different kind of feature. And what we're showing here is that for every gemoscope feature from like a regular SAE that's been released and out for about a year now, we can find basically an equivalent feature representation that encodes much the same concept to some degree. These aren't exactly equivalent features, which is to be expected given that it's an unsupervised method that has no guarantees about what it will recover. But nothing really seems to be lost going from the prior SAE architectures to this contextual versus novel factorization, at least. So you can also consider doing something like explicitly measuring whether the novel codes are tracking the fast-moving new information at any given time step, and whether the contextual part is capturing slow-moving contextual information slowly being built up over time. So the intuition here is a little bit fuzzy at first, but basically what you can do is take these activations across temporal positions and do a Fourier transform on this vector to get a series of like low frequencies and high frequencies. Intuitively, low frequencies across time mean that it's more slow-moving information that doesn't change a whole lot as you move throughout the sequence. High frequencies imply that it's changing very rapidly, and thus maybe is a good proxy for something like novel information or fast-moving information. We can simply divide these frequencies in half at the midpoint and take everything below this cutoff as the slow-moving parts, the slow frequencies, versus the fast-moving parts, the high frequencies. And we see that when we try to reconstruct these two different parts of the representations using our temporal versus novel codes, on the left-hand side of this graph, we see the predicted code or the contextual code tracking the slow-moving information pretty well, and the novel part tracking the fast-moving information pretty well. Whereas regular SAEs only seem to be tracking the fast-moving information, but are also kind of going off track because they're kind of trying to do both things at once, as indicated in this like blue line corresponding to the relevant architecture here. It's kind of getting a mixture of information and not factorizing it very well at all. So qualitatively, this all seems like it's working pretty well. And unfortunately, I do just have a lot of qualitative analyses to throw at you because intrinsically evaluating these is quite hard. But I think what I hope to make the point of in this next section is that these actually add to our understanding of what's happening inside the models relative to prior featurization methods. So we can start by doing something like the garden path sentence example here. So given this garden path sentence, you might initially think that when you see the old man, that man is part of a noun phrase, the subject of the sentence. But then you see the full rest of the sentence, and you realize that it was actually the verb, the old are man in the boat. This is pretty challenging for humans to process. And of course, many language models also struggle with garden path sentences. But we expect that state-of-the-art models are able to parse these pretty well. So looking at the hierarchical clusters formed by the activations of the SAEs on this sentence, we see that all of these left three figures do give you the parse corresponding to the garden path sentence parse. It's clustering man as being more similar to old, which implies to us that it's representing this as basically being part of the noun phrase, as opposed to the actual verb that it is. And the novel codes act much the same way because they are very SAE-like. But the contextual information, which is able to take into account everything that it's seen thus far, does give you the correct parse here. It clusters the word man as closer to the objects, as opposed to being closer to the original subjects. So it seems like it actually is capturing this more relevant syntactic information here in a way that a human might expect after having seen the full sentence. You can also imagine giving it a control sentence, which isn't a garden path sentence. Oh, I think there's a typo here. This should be the sailors and the boat, so it's actually grammatical. In this unambiguous input, where you would expect man to always be the verb phrase, you still see that these SAEs are putting man as closer to sailor. So even though man here is obviously not a noun, these SAEs treat it as if it were. Whereas the predictive information in these temporal SAE codes do seem to cluster man as generally being closer to its object than to the subject, because that's what it actually is in the sentence. So we seem to have a bit more contextual sensitivity here, which is nice. We can also do something like decomposing event boundaries using these representations. So given a story like this, there are various sort of turning points, after which the activations should look pretty similar to what came before them. So you have this like generated story that we just generated via like Claude, for example, which we tried to prompt it to say something like, generate a story that seems to have like one part, and then a second part that's like completely different in every possible way. And it really fit the bill, I think. So obviously, I think any SE should recover the fact that Python code is very different from text. But also, even within this first few part of the stories, you should see some pretty big distinctions in how the model treats these activations, because different things are happening here. So if you were to make some independent assumptions, as most SAEs do, you probably wouldn't see any kind of meaningful block structure. So what I'm showing here is the autocorrelations of each activation to each other activation across positions. Where what you would expect to see is like this block structure that corresponds to the event boundaries in the story. So with regular SAEs, you do see some evidence of this block structure, but really what's happening here for the most part is that they're tracking like the information at any given token position pretty independently, so that there really is no block whatsoever for like top K or batch top K SAEs. But the predictive codes of the temporal SAE do seem to capture this block structure, even if only quite roughly and not perfectly here. We tried quantifying this as well, just to make sure that everything within blocks had higher correlation than everything outside of the blocks. And we do see this actually does hold for the predicted codes at least. So you can also do other kind of cool qualitative analyses here, like tracking how the representation of a single word changes over time. So for example, across the story, the representation of a given word should be changing depending on its context, you would imagine. Most SAEs make this independence assumption and exchangeability assumption. So the structure here should be somewhat random for those SAEs, which is what you do sort of observe in these visualizations of the top principal components of these activations. But on the right-hand side, the predicted codes do seem to follow a pretty clear linear path from the beginning to the end of the story. This isn't necessarily strong quantitative evidence, but it does seem to suggest that the geometry of these representations is tracking in a way that is probably closer to what we would expect to see. And if you cluster them again, the main axis of variation for the predicted codes is a long time. You see there's basically this very clear sorting of every word in the sequence according to when it appeared. Whereas for regular SAEs, the clusters have basically everything to do with the individual word's meaning by itself. So the bottom cluster seems to be more like a bag of words clustering. Whenever the same word appears, regardless of its context, it's always going to appear in the exact same cluster with itself. Whereas for the predicted codes, you're always going to see something more like this arrangement according to like where it appeared in the context, which is the desired behavior here. We'll just skip this part because I think we're running a bit low on time now. But the main point that I want to show throughout this whole talk is that language and representations are clearly non-stationary. So in this project, we showed that by incorporating these time-aware inductive biases into our interpretability methods, we were able to significantly improve the explainability of those representations themselves. So for those of you who are interested in inductive biases and have maybe been a bit dispirited by the bitter lesson lately, I feel like interpretability is an area where you actually still can innovate on these inductive biases. Because ultimately, if your goal is to explain rather than to merely improve engineering performance, you actually do have to consider the structure of the data that you're trying to model in most cases like these. And in terms of the temporal SE that we introduced here, it seems that the predictive codes are really good at tracking this slow-moving information in a way that's faithful to the model's actual representation of the sentences. So things like parses and event boundaries, even in ambiguous inputs. Whereas the novel codes are acting a lot more like traditional SAE features. We believe this factorization will give you results that are much more faithful to the actual model's behavior and could improve our ability to explain the concepts underlying the model's computations. Zooming up even further, I think that in general, if you want to explain the behavior of a language model or language itself in general, you have to consider the incremental construction of the representations of language. The whole idea behind language is that you're expressing fully formed meanings in a one-dimensional manner across this temporal axis. And so to actually understand like the way that humans would express meaning in that way, you have to consider the medium itself. I think also the big takeaway here is that we should be making more assumptions and stronger assumptions in many cases of the structure of our data sets. The weaker our inductive biases and the more general they are, the more we're likely to miss this really important underlying structure. I guess in a way you could perceive this as actually weakening the assumption of stationarity, but I also see it as a case of like improving our inductive biases to more closely resemble the structure of the target of our models. One thing I want to note here though, is that even though we were able to find evidence of a lot of interpretable representations, I don't mean for this to be a call to interpret things in a human-like manner in these models. I think much like people studying animal cognition, you have to be very, very cautious as to what you can claim the model understands or has learned. You should instead try to understand the model on its own conceptual terms. And I think by being more faithful to these models' architectures and our interpretability methods, we can get much closer to that ideal. So yeah, this was a project that was conducted in collaboration with a lot of cool collaborators. And I'd like to give a brief shout out to all of them here and to you as well for listening. Thank you. Yeah. Yeah.
So do you observe this phenomenon on all layers SAE?
Yeah, so this result was obtained by looking at just the middle layer. We chose that one because it's hypothesized to have like all of the important abstraction in the input sequence in a way that is non-trivial. So early layers tend to be more like token detectors, and late layers have features that are more like token predictors, which are both kind of trivial in a way. But the middle layers have the most abstract information. This is what we've been finding so far in the literature. We should pick that one. I hypothesized that if we were to extend this analysis to other layers, we would find similar trends, but we didn't in this case. Yeah.
Do you have any thoughts on like how these things may be applied, like especially in light of things like, as you mentioned, the bidder lesson, and also like, I know I've seen some works that have shown like SAEs fail to beat like simple baselines with like applications. So I don't know, do you have any thoughts on that?
Yeah, so I think if you know the concept you're looking for, like you will definitely always do better by using a supervised method, like a pro or like causal abstraction. Because you actually have like a signal that you can optimize towards, and you can give maybe more strong guarantees as to the accuracy of your methods under greater like amounts of data. With unsupervised methods like SAEs, I think the comparison is a little bit unfair because the goals are a bit different. So for example, if you don't really know the concepts that are in the model and you don't know what you're looking for, you basically have to use unsupervised methods. And so the comparison to supervised methods becomes a little bit like fraud when you start making that assumption of not knowing what's there. But within unsupervised learning, because there's nothing to directly optimize for rather than reconstruction, it becomes basically essential to like engineer this inductive bias. And I think this actually is true of basically any method that's trying to learn from like not super clear labels. So like the more your inductive bias resembles the true structure of like within your modeling, I think the better you'll do at recalling all of the important concepts in that latent instance. I think those may be two orthogonal answers, but did I get your question?
Yeah, you did. Thank you.
So does temporal coding also share the same limitations of essays? Like we don't know what exactly is being disentangled and what concepts we know that it's optimizing for sparsity and feature reconstruction, but we don't really know what the outputs are.
Yeah, like you basically have to do analyses of like the like dimensions themselves to be able to say what they are. And again, like there is basically no guarantee of recovering any particular concepts because it isn't supervised. We did find, and a result that we did include in the paper, that these temporal SAEs seem to be a bit more stable across random seeds than regular SAEs. We don't really know why that's the case, but we think it has something to do with the fact that this factorization preserves like more of a true taxonomy of like the representations in a way that regular SAEs do not enforce. But we don't actually know for sure what's happening here, unfortunately. So yeah, basically the pipeline is sort of the same whether you use this or regular SAEs. You can decompose it, but then you still have to find the right features that influence your task, and you still have to interpret them yourself.
And is it easier to track these across layers and match feature from layer L to L+1?
Yeah, I think like any methods you could apply in SAEs would apply equally well to these two. Like you can imagine discovering like a circuit over feature representations. Whether you're using like SAEs or transcoders or like temporal codes. I think is always possible. I think the main benefit here is that you would know something about like what the feature should contain when you attribute to a temporal like novelty code versus a contextual code. If you have a contextual code that's really important, then you know that the important information likely came from like somewhere much earlier in the context. But if there's like a novel code that's in your circuit, then you know that like information right here at this position what was caused the model to do something. And I think it's a pretty helpful signal.
So in SAE, some of the weird pathologies that you see with features are things like feature splitting or feature absorption or having a lot of copies of features and so on. Once you move things into like the temporal setting, what do you think feature splitting or absorption looks like?
Yeah, that's a good question. Honestly, I'm not super sure, but my sense is that if your dimensionality is too high in your latent space, you should still see a lot of feature splitting. I think this happens mainly because, as we've been discussing a lot today, actually, I don't think that directions are actually like the right abstraction for concepts in language models. I think it's probably more of like a bounded manifold. And directions are practically useful for like approximating like going toward the manifold, but you also don't really know how far you have to steer to like stay within it or like when you actually leave it. And so you never know like what steering is going to give you like degenerate behaviors or not cause the concept to appear at all or anything like that. And a consequence of this is that you can change the dimensionality basically like to infinitely high, and you'll always be able to split the direction into like more and more separate directions, corresponding to like different like angles from the origin to like points in your manifolds. Especially if it's very kind of like blobby looking and goes in a lot of different directions. Just a hypothesis. But I think that a lot of recent work has been supporting this notion of concepts as like convex holes lately. So that's my current working theory of what's happening.
Yeah, like is steering temporal code like more in distribution compared to steering like essays?
I think related to the previous answer, probably not. I think that they're both kind of OOD in the same way. So like the main benefit of the temporal codes here is like, I think the factorization of information into like meaningful parts. But I think like any issue that has to do with like the geometric assumptions of SEs would still hold equally validly for temporal codes. Because we're still assuming that concepts are like directions. And I think that's maybe where like the fundamental flaw lies here. Like we do it because it's a very useful abstraction, it's very fast to learn. And like learning convex holes and predicting on them is like really, really slow. So I think it's a valid trade-off to just assume other directions, but ultimately, like this is the source of all of these issues, and we don't really address those here. Yeah.
I was wondering about your autocorrelation hierarchical clustering experiments, where I think you were working on the SAE representations. So if I understand it correctly, I was wondering how do these perform if you would just directly use the transformer encodings? I guess from the middle layer, it sounds like you're focusing on. My impression of the more the encoder-only transformer literature suggests at least some of these might work, but I don't know how well it's been explored.
Yeah, so I think like to get this correlation to actually look as good as it does, you do have to factorize out the contextual slope of the information from like the novel parts. Because if you mix them all together, then so we actually plot like the representations across different positions. And what we see is that for the activations, the left-hand side here, things do still look like pretty blobby and like this very high dimensional like rotating structure. Whereas for the predictive codes, there's a really clean separation between like the user and assisted tokens, such that like you can basically factorize out like when the split occurs. And in the predictive codes as well, you also see this like pretty clean pathway from beginning to end of sequence. So it seems like focusing on that part of the representation specifically is what gives us our gains here. And activations probably will perform probably similarly to the other SEDs here given this structure, I would imagine.
Just quick clarification, are each of these just activations of like a single token and input?
Yeah, we just started them on like the top two like PCA components.
Oh,
yeah.
Were there any questions from anyone coming online? If not, then once again, I'd like to thank our speaker for stop today.